yesterday, we talked about what a derivative tells us about what the graph looks like, right? Now, last class, we talked about the increasing decreasing test, which is like the dumbest name for something because we already know what the derivative being positive or negative tells us about the shape of a graph. And I told you that you could either memorize how to do every single question in this section, or you can just think about what is going on, right? So I gave you the tools to memorize it if you would like to, but it's a lot easier to just think about what you're plugging things into instead of just being like, okay, I have to plug things into this function. I have to do this. I would stray away from that mindset because there's a lot of stuff to memorize in this class already. So let's kind of stray away from that. Now I told you to find, oh, yeah, you're okay. There you go.
Thank you.
Mhm. All right, now I told you to find increasing and decreasing intervals. First of all, we found the critical values because those could be local mins or maxes, right? So those are the places we look for local mins or maxes. And I also told you that you had to find places where the original function didn't exist because, well, we can switch from increasing to decreasing at a vertical asymptote, for example. Okay, so that was something to think about. We set up our chart and so on, and we found our intervals of increasing and decreasing. Okay, we're going to move on to a different type of question today. Now, when we talked about critical numbers, I kind of already gave it to you, so I'm not going to ask you. We said that critical numbers are the places where we think might be a local max or a local min. Now, we haven't really actually found those values, so let's talk about how we can use critical numbers to figure out things that we're interested in. And to do that, we have this cool thing called the first derivative test. Okay, now, let's just talk about what the first derivative test says, and then I'll kind of explain to you why you might not have to memorize this entire big test here, okay? Let's just say that C is a critical number, so it's either where the function doesn't exist or, where the derivative doesn't exist or where the derivative equals 0, but the function has to be defined there, right? If the derivative changes from positive to negative, increasing to decreasing, then the function has a local max at C. That makes sense because we're going from increasing, going up, to going down, right? On the other hand, if the function goes from decreasing or the derivative being negative to increasing, the derivative being positive, then we have a local minimum, right? That seems to make sense too. Okay. Now, let's say that, okay, the derivative is positive to both the left and right. So that means we go from increasing to maybe increasing. And if we have a critical point, this is what it would look like. Okay, then there's no local min or max. The same thing if the sign stays the same to the left and the right. Okay, so I know this is a lot of words. It's saying something very simple, right? If we go from positive to negative in the derivative, local max, negative to positive, local min, okay? You can either memorize this, okay? See, oh my gosh, I need to twist this in. So you can either memorize this, okay? Or you could just think about what it's saying and piece together the meaning of increasing and decreasing, okay? All right, let's actually put this together in an example and see how this plays out. Okay, so in this example, we want to find the local min and max values of our function 3x to the fourth minus 4x cubed minus 12x squared plus 5. This is the same function as example 1. Okay. With this type of question, we're just dealing with critical values, not the places where our function doesn't exist. Okay, only dealing with critical values. So let me write a note up here. Only looking for critical values, not discontinuities. Okay, this is a little bit different than example 1 and 2 because we're not looking for places where the function doesn't exist. We're strictly looking for critical values. Okay, now since this is a polynomial, doesn't really matter, but the next example it might kind of matter. Okay, now what we're going to do, we're going to find our critical values. We're going to set up our chart, figure out where the derivative is negative, where it's positive, and I think we already did that, right? In example 1, we found our critical values to be 0, 2, and -1. We also set up our chart, and because I'm lazy, I'm gonna do this. I'm gonna take my chart of critical values. I'm going to copy it, and I'm gonna paste it here. Haha, there we go. So this is literally what I wrote in the last page. Now I know you can't do that on your paper, but that's a little bit too bad, isn't it? Okay, so we have our critical numbers here. I know that we're decreasing below -1, increasing between -1 and 0, and so on. Okay, let's find our maxes and mins. Well, let me use a different color for this. I know that I go from decreasing, which means the function looks like this, to increasing over here. Okay, is -1 going to provide me a local max or a local min? Min, right? We go from decreasing to increasing, which you can either memorize means a local min, or you can just draw a picture and look, okay, it looks like a U, that's a local min. Okay, from at 0, it looks like we go from increasing to decreasing, local max, right? And then from at 2, we go from decreasing negative to increasing positive. So that's also a local min. Okay, here's where things get a little bit tricky. Can I say that -1 is my local min? So that, would that be correct? I'm gonna tell you it's not correct.
It's local, but it's not absolute.
Oh yeah, it's not absolute, but is -1 my local min?
Oh, no, -1 doesn't exist.
-1 is a critical value, so the function exists at -1. Is a local min an x value or a y value? So y value, right? So you were right when you were like, okay, it is a local min, but saying that -1 is a local min is not correct, okay? The way that I write my local min, okay, I could say f of -1, that would work, okay? I could also plug -1 into my derivative or my original function. Which one am I plugging into? The original function, right? My function value at -1 is my local min. So I could say f of -1, or I could do this. 3 times -1 to the 4th minus 4 -1 cubed minus 12 -1 squared plus 5. And to save you some calculations here, I'm getting 0. Also, don't trust my calculations. If you do this at home later, you might get a different answer. So either f of -1 or 0 is my local min, not -1, okay? All right. Also, another local min is f of 2, right? So you can either say f of 2, or you can plug 2 into the original function, minus 4, 2 cubed, minus 12, 2 squared, plus 5. And I'm going to tell you that that is -27. Okay, so I got 2 mins, 0, -27. I didn't leave enough space to do my local max, so let me do it here. Okay, my local max would either be f of 0, or you can plug 0 into the original function, which gives me 5. Okay. Now, on WebAssign, I would definitely plug it into the original function. I don't know, WebAssign will take f of -1. I don't think it would like that. So if you're doing the homework and you're looking for a local min or max, I would definitely type in the actual number, okay? All right, any questions on example 3? All right, but you know what's coming next. If you turn your page to example 4, we're going to take a look at example number 2 and find the local mins and maxes of example number 2. Okay, now if you weren't here yesterday, if you don't have this copied down, I'll leave the chart for example 2 up here. Okay, example 2, this example is a little bit tricky. It's a little bit different than the last one because we had a discontinuity in this example. Okay, so think about that. Might not change your answer at all, but something to think about. Okay. Looks good. All right, I know it's kind of weird flipping back and forth between the pages, so I'm gonna actually do this in front of the class because I want to talk about something real quick. I'm just gonna copy my chart here and then paste it over here. Okay. In this example, we had we found our critical numbers, right? We got -2 and 0, and -1 came about, but we said that the function didn't exist at -1, which is why we kind of threw it out as a critical number, but we still kept it because increasing and decreasing also, we also have to think about where the function doesn't exist, okay? So the only critical numbers in this example are -2 and 0, but not -1. Okay. Now let's just take a look at this chart. Okay, now when we're dealing with local mins and maxes, we don't deal with places where the function doesn't exist because those aren't critical numbers. So I'm just going to throw this -1 out. Okay, we're not even thinking about -1. Can't be a critical value, even if the sign changes between them. Okay. All right, so at -2, looks like we go from positive derivative, which means we're increasing, to a negative derivative, which means we're decreasing. So is f of 2, or sorry, is f of -2 a local min or a local max? Local max, good. Okay, now if I wanted to find the number, am I going to plug -2 into the derivative or the original function? To the original function. I want to find f of -2, which means I'm plugging -2 into the original equation in the question. So I'm going to plug this into -2 squared over 4 times -2 plus 4. This should give you -1. Okay, so your local max is -1. All right, let's go into 0. It looks like we go from negative derivative, which means we're decreasing, to a positive derivative, which means we're increasing. Looking at the picture I just drew, this is obviously a local min, right? So we have a local minimum at f of 0. Okay, plugging that into the original function gives me 0 squared over 4 times 0 plus 4, which is 0. Okay, so on WebAssign, I would type in -1 as my max and 0 as my min. Okay, let me just talk a little bit about this question. I know this one was kind of easy because even though we threw out the discontinuity, it wouldn't have mattered since the sign stayed the same. Let me just show you what would happen here. Let's say I had my chart, so I had my number line. So this is like an alternate scenario. Okay, and I had my -2 and 0, but at -1, I still had a discontinuity, which means my function doesn't exist there, okay? If my derivative went from positive to negative here, would this be a local min, or sorry, a local max? No, right? Because discontinuities don't count as critical numbers, okay? So even if this happened, which it could happen, this would not be a local max, okay? Not a local max. Okay, local maxes and mins only happen at critical numbers, okay? All right, any questions on example 4? All righty, let's flip our page over to the next example. Now, I know I kind of used the previous examples to find local mins and maxes, but I really do want to piece everything together, just so you would know what to do if you were asked to find a local min or max without like finding increasing and decreasing first. So let's go to this example. We also haven't dealt with trig yet, so let's do this as a refresher. Let's see, we want to find the local max and local min of x plus 2 times sine of x on the interval 0 to 2 pi. Okay, so we want to find the local maxes and mins there. Okay, First of all, we have to find our critical values, right? So we got to find the critical values. Okay, we're not looking where the function doesn't exist. In this case, it doesn't really matter, but that's okay. Okay, to find critical values, first we have to find the derivative. Can someone tell me the derivative of my function? 1 plus 2 cosine of x, good. Okay, so critical values are where my function either equals 0 or where it doesn't exist. Let's do equaling 0 first. So setting my derivative equal to 0 gives me 1 plus 2 cosine of x equals 0. Okay. Guess I got to subtract 1 from both sides to get 2 cosine of x equals -1. And then dividing by 2 on both sides, I get cosine of x equals -1/2. How do I solve this?
You just know, if you know where, the cosine in 1/2 is, which is, 2 pi/3 and 4 pi/3.
Awesome, nice. And I also heard inverse cosine, right? So there's actually 2 ways you can go about this. It's basically the same way, but you can either do the inverse cosine of both sides, right? Okay, so you'll get x equals inverse cosine of -1/2. Okay, you can type this into your calculator, but I'm pretty sure your calculator is only going to give you one answer. Okay, so doing inverse cosine is okay, but if we're on a bigger interval, Michael's method might be a little bit better. Okay, so this will probably give you 2 pi/3 in your calculator. It won't give you the other one in the interval that you want to find. Okay, so this is way 1. It gives you one value.
It gives you like a decimal value, so it gives you like 1 point of something.
Oh, really? Okay, yeah, maybe that's not the best way then. Yeah, it gives you one value, but it doesn't give you like the other one that you're interested in. So the other. Way 2, let me write this in a different color. Okay, is to just think about what value or values of x make cosine of x equal to -1/2. Okay, now the way I like to think of it is the unit circle, right? Drawing our unit circle, we want to figure out, okay, where are my x values or the x coordinates equal to -1/2? Well, that would probably be, I don't know, maybe this angle and this angle. And using our knowledge of trigonometry, this angle is 2 pi/3 and this angle is 4 pi/3. Okay, so there's 2 places where the cosine of x is -1/2. All right. Any questions so far? Good. Okay. Now I'm not going to find any more angles because we're only interested between 0 and 2 pi. Okay, so the 2 critical numbers I'm getting here is x equals 2 pi/3 and 4 pi/3. Okay, those are my 2 critical numbers. Now, my derivative doesn't exist. Well, actually, there's no places where my derivative doesn't exist, so I don't have to think about that. And that pretty much covers it for my critical values. Okay, so these are my critical values. All right, now we can set up our chart. I know I didn't give enough space for the chart. I'm sorry, but let's try our best to fit everything in this chart. Okay. All right, we've got 2 pi/3 and we've got 4 pi/3. Okay, I didn't give any space for anything less than 2 pi/3, but that's okay. Okay, we want to set up our chart and figure out what our function looks like between the intervals. Okay, now can someone give me a number less than 2 pi/3? Okay, 1 would work, but pi/2, what's the easier one?
5/3.
Okay, what's easier than pi over 3? 0. 0 is a lot easier, right? Now you can choose pi over 3, that's okay. But I'm lazy and I like to plug in 0 when I can, okay? Now, can I plug in anything less than 0? Well, take a look at the question.
What was that?
Oh, no.
Yeah, I'm looking at the interval 0 to 2 pi. So, okay, also if I go less than 0, you're gonna get numbers that look a little bit wacky because the unit circle goes in a circle, it repeats itself. And if you go below 0, you're actually going below 2 pi, which would put you in the other interval. Okay, so let's choose x equals 0 because I'm lazy and I don't feel like plugging in pi over 3. You guys want to make me work really hard today. Okay, and what am I going to plug 0 into? The derivative or the original function?
The original- oh, no, the derivative.
The derivative. Why are we plugging into the derivative? Yeah, the reason I'm setting up this chart is I want to figure out if the function is increasing or decreasing in this interval. The thing that tells us if we're increasing or decreasing is the derivative, not the original function, okay? So you can either memorize for this question to plug into the derivative, okay? Or you can think about the final goal. The final goal is to figure out if we're increasing or decreasing. The derivative is what does that, okay? So I'm gonna take my derivative, which ended up being 1 plus 2 cosine of x, right? 1 plus 2 cosine of x, okay? Guess I'm gonna plug in 0. Okay, what's cosine of 0? 1, good, so this would be 3, okay? Is 3 positive or negative? Positive, that's a dumb question. So are we increasing in this interval or decreasing? Increasing. Positive derivative means we're increasing. Okay. All right, can someone give me a number in between 2 pi over 3 and 4 pi over 3?
Pi.
Pi is a good number. See, that's the numbers I like, the ones that are easy to plug in. You might have to pay me a little bit extra to plug in weird ones. Let's plug in x equals pi. All right, so we're plugging this into the derivative. So I'm going to do 1 plus 2 cosine of pi. What's cosine of pi? You always use your calculator.
Oh, 0.
Not 0.
Oh, and
Think about the graph of cosine. It looks like this, right? And it goes from 0 to 2 pi. Pi is in the middle. I hear -1, right? My point down here is at -1. Okay, so that's kind of how I think about the values of cosine at the quarter angles, okay? So cosine of pi is -1. So this is 1 minus 2, which is -1, okay? So that means we must be decreasing here. Okay. All right, finally, can you give me an easy number bigger than 4 pi over 3?
2 pi.
2 pi. 2 pi is the number that I want to hear because it's easy to plug in, easier than the other ones, right? So let's plug in 2 pi. Okay, we'll do 1 plus 2 cosine of 2 pi. What's the cosine of 2 pi?
1.
1, good. Remember, it's the same as cosine of 0. So that's 3, which means we're increasing. All right. Now, we're not done yet because we have to figure out what our local mins and our local maxes are. Okay, let's think about 2 pi over 3. At this point, we go from increasing to decreasing. So do I have a local max or a local min?
Increasing. So max.
Yeah, right. If I drew it, I'd be going up and then I'd be going down. So that's a local max. Okay, so that means we have a local max at 2 pi over 3. What mistake did I make there? Actually, I'm not going to tell you that. What's my mistake here? Local max is 2 pi over 3. That's an x value, right? My answer has to be a y value. So I can either say it's f of 2 pi over 3, or I could plug in 2 pi over 3 to what function? The original function or the derivative? The original function, right? So 2 pi, f of 2 pi over 3, or 2 pi over 3 plus sine of 2 pi over 3. Okay, now you probably don't want to do this. What's sine of 2 pi over 3? Oh, it's 2, right? Yeah. What's sine of 2 pi over 3? Thinking hard.
√3/2.
√3/2, good. Okay, so my local max is 2 pi over 3. Oh my goodness. Plus √3. Okay, so WebAssign probably won't take f of 2 pi over 3. I would take it on a test or quiz, but this would be the number you type in for like WebAssign or something like that. Okay, so that's our local max. Let's do our local min. Okay, so local min. Oh, I didn't even tell you it was a local min, didn't I? All right, well, we go from decreasing to increasing at 4 pi over 3, so it looks like that's going to be a local min. So you can either say f of 4 pi over 3, or you can plug it in, right? So 4 pi over 3 plus 2 sine of 4 pi over 3. All right, here's where we got to think a little bit. What's the sine of 4? Oh my gosh, of 4 pi over 3.
-√3/2.
Negative √3/2, good. So plus 2, negative √3/2. So this would be 4 pi over 3 minus √3. Okay, so that is my local minimum. All right, now I did put the graph of the function here. So I drew the original function in this little box here. I actually didn't draw it, the textbook did. But it looks like at 2 pi over 3, we do have a local max. And at 4 pi over 3, we do have a local min. So it looks like we did a good job of finding those two. All right. Any questions on example number 5? All right. I want to talk about something real quick, and then I'll let you do the quiz. Okay. Moving on to the next page. This page is actually something that we did before. Okay. So I literally just screenshotted the notes from a while back when we talked about concavity, and I just stuck it in these notes again. Okay. Now, if you kind of recall from a while back, we talked about concave up versus concave down. Does anyone remember what that meant about the graph of a function? Sam?
Concave up is like, it's like when the function is going to meet you, and the concave down is like when it's below the function. It kind of helps with like integrating and stuff like that.
Yeah.
Finding what's.
Yeah, I see. I think you're in the right you're in the right mindset there. Concave up is when the function looks like a cup, right? Concave up like a cup. And concave down is when the function looks like a frown, right? It's going down. Concave down like a frown. Okay, so that's the way I like to memorize it. If the function is facing up, then it's concave up. If the function is kind of facing down, so it's opening towards like the negative values, it's concave down. I like to think of it as a cup or like a frown. Okay. Now we talked about how the second derivative has to do with concavity. Does anyone remember what the second derivative tells us about concave up versus concave down? What happens when the second derivative is positive? It's actually right up here. So when the second derivative is positive, we're concave up. When the second derivative is negative, we're concave down. Okay, so that's what the second derivative told us about. What happens when we switch from being concave up to concave down, like at this point right here? No concavity, good. Do you remember what we called it? Starts with an I. Points of inflection, good. When we switch from up to down, we call it a point of inflection. Okay, So we'll pick back up on this next class, but I think we have a quiz to go over. So why don't we go and do that?